Welcome everybody. This is the second part 2 of the second lecture of week 4, and we're now going to consider the relationship between two random variables. So up till now we've been talking about single random variables, and we talk about them being characterized by a probability distribution and having main characteristics mean, median, and variance. Now we're going to look at what happens when we have two random variables and how they affect each other, and we're only going to look at the very simplest relationship between two random variables, and that is, we'll see shortly, the degree of linear dependence between the two random variables. So this section is going to be called covariance and correlation, and as I mentioned, we consider two random variables now. We'll call them x and y. We're assuming that we know things about both x and y, so their mean and their standard deviation. And then we can ask, what is the relationship between x and y? So some examples. An example, I suppose, is that if we took a series of observations or realizations of x and y and then plotted the pairs of points, I might see something like this. And if I do see something like that, it's basically saying that as x is increasing, y also tends to increase. So there's some sort of relationship between x and y. If I know what x is, I know more about what y is doing. And so we say then that x and y are independent, are dependent. In fact, in this particular, if we see this thing up here, we can say that the x and y are positively correlated. So to capture this idea of dependence between x and y, we're going to define something we're going to call covariance. And I write this as COV brackets x comma y. And we'll see shortly that this is the degree of linear dependence between x and y, and I stress the word linear here. Covariance between x and y could be 0, and yet there still may be a strong nonlinear dependence between x and y. We'll see an example of that shortly. So this thing is only going to capture the degree of linear dependence. So if this thing is showing a straight line trend, it'll show a positive covariance. But for example, if I saw something like this, I plot my pairs of x and y and I see something that looks like this, well, clearly there's a strong nonlinear relationship, but the line of best fit here might just be a straight line that looks like this. And that straight line is a constant, so that y equals a constant has no dependence on x. So that particular line of best fit says that there's no linear dependence between x and y, but clearly there's a nonlinear dependence. So just because covariance is 0 doesn't mean that x and y are independent. There are some situations where it is true that if covariance is 0, then x and y are independent. For example, if they're log normally distributed. But in general, the covariance of 0 does not mean that they're independent. Okay, so as I mentioned, it only captures the degree of linear dependence and not nonlinear dependence. So it's really the first measure of a relationship between x and y. Okay, so we're going to define covariance using the mathematical definition shown here. It's the expected value of x minus its mean times y minus its mean. And so we can see here, if y generally increases as x increases, then covariance of x and y will be positive. In other words, if x is bigger than mu of x, then y will tend to be bigger than mu of y. So I got a positive term times a positive term, which is positive. If x is smaller than mu of x, then this thing tends to be negative, and y tends to also be smaller than mu of y. So this also tends to be negative, so negative times a negative is positive. Okay, and alternatively, if y decreases as x increases, then the opposite happens. If x is big, this thing is positive, but y will be small, and this is negative. So positive times negative gives negative, and vice versa. If x is small, y is big. And that product, again, becomes negative. In general, the sign of the covariance is the sign of the slope between x and y. So if I see something like this, then the covariance is going to be negative. If we look at this definition in a little more detail, covariance between x and y, expected value of x minus its mean times y minus its mean, I multiply it all through, I get expected value of xy minus mu of x times y minus x times mu of y plus mu of x times mu of y. This is the expectation of a sum, which we mentioned before is just sum of expectations. So I can break it up at the plus and minus signs. Expected value of xy minus expected value of mu of x times y minus expected value of x times mu of y plus expected value of mu of x mu of y. The constants inside each of these expectations can just come out. This is an integral, so constants and integrals come out front. So I get that coming out, and here I bring out that constant. I just get the expected value of 1, which is 1. So that expected value of a constant is just, of course, the constant. Okay, so I get expected value of xy minus mu of x times mu of y minus mu of x times mu of y plus mu of x times mu of y. So it boils down to expected value of xy minus mu of x times mu of y. And I usually write this as follows. Covariance between x and y is expected value of xy minus expected value of x times expected value of y. And in fact, if we look at this equation that we've shown here, and we say, okay, let's let, I probably should have written it the other way around, let y is equal to x. And in this case, then y is completely linearly dependent on x. Then this equation here becomes covariance between x and y is covariance between x and x, which is expected value of x squared minus expectation squared of x, which we know is the variance of x. So basically, if we have complete linear dependence and compute the covariance between x and itself, this is just the variance of x. I see I've got a mistake here. This is not, this is actually correlation coefficient. Let me just write that down. Correlation coefficient. So let me just, I need to correct this. The coefficient of variation, of course, is just the sigma over mu. Okay, so we're going to define the correlation coefficient to be the ratio of my covariance divided by sigma x times sigma y. And basically what I'm doing here is I'm taking out the sort of variance term. We know that when they're perfectly correlated, the covariance between x and x is sigma x times sigma x, which is variance of x. So if I divide by that thing, I get this this form here. So rho xy is covariance between x and y divided by sigma x times sigma y. And we can show that this correlation coefficient must lie between -1 and +1. And the closer it is to either endpoints means a stronger linear dependence between x and y. In particular, if y is equal to x, as we had above, then the correlation coefficient between x and y becomes the correlation coefficient between x and itself. I get the covariance between x and itself divided by sigma x times sigma x, which is variance of x divided by sigma x squared. And of course, variance of x is just sigma x squared, so this ratio becomes 1. In other words, x is perfectly correlated with itself. So as I mentioned, the closer rho of x is to plus or minus 1, the stronger the linear dependence between x and y. So I could draw some pictures here. If I saw something like this, I'd say that's reasonably strong linear dependence between x and y, but it's negative. Okay, so as x increases, y tends to increase. I would guess the correlation coefficient for this would be something like -0.9. If I saw something like this, even stronger linear relationship between x and y, but now it's positive, I would guess the correlation coefficient would be something like plus 0.95. If I saw something like this, there seems to be very little relationship between x and y, so I would suggest the correlation coefficient is close to 0. And in fact, we saw this earlier, if we saw something like this, it means y is basically non-random, and it's equal to a constant, so independent of x. So the correlation coefficient here is 0, even though this is this is close to a straight line. But in this case, the straight line is not dependent on x, so rho of x is equal to 0. Okay, so let's illustrate this by an example. Let's suppose that y is equal to a plus bx. Again, that means y is completely linearly dependent on x, so we should expect the correlation coefficient to be equal to 1. And let's assume in this case that b is greater than 0, and that's why we have a plus sign here. This is the slope b is positive, and so we should get a plus 1 for the correlation coefficient. Okay, so let's just step through the details to solve this. We already know what the answer should be. Let's just make sure that the math tells us that. So covariance between x and y is defined as the expected value of x minus its mean times y minus its mean. And now I can write expected value of x minus mean and then replace y with what it's equal to. So a plus bx, the mean of y then is the expected value of a plus bx. Okay, and then everything inside the expectation operator. Okay, let's look at one piece at a time. Let's look at this piece here. Expected value of a plus bx, as I mentioned, expectation of the sum is just sum of expectations. So it's expected value of a plus expected value of bx. Well, a is a constant, so its expectation is just equal to the constant itself. The b can come out front, so constants can come out, and I get b times expected value of x. And expected value of x is just mu of x. So a plus b, so expected value of a plus bx is just a plus b times mu of x. And that, of course, is just mu of y, which is what we have here. So plugging that into our expression up here, we have covariance between x and y is expected value of x minus its mean times a plus bx minus a minus b of mu of x, b times mu of x. Now let's collect terms. We see that the a's cancel in here. I get a bx minus b mu of x, so I can take the b out. I can factor it out, put it in front here. I get expected value of b times this thing, x minus mu of x. And in here, I'm just left with x minus mu of x as well. So the b is a constant. I can bring it out front. I get b times expected value of x minus mu of x quantity squared. And we know that this is the variance of x. Okay, so this boils down to b times sigma x squared. Okay, to get the correlation coefficient, we divide our covariance, which we have already determined here, divided by sigma x times sigma y. So we still need to find sigma y. I'm assuming sigma x is known. Okay, sigma y is the variance of y, which is the expected value of y minus its mean quantity squared. And we already saw the y, since it's equal to a plus bx, and its mean is a plus b mu of x, this quantity here is a plus b of x minus a minus b mu of x all squared. So the a's cancel again, and I'm left with b of x minus b mu of x quantity squared. The b can factor out, and it becomes b squared, and I can bring it right out front of the expectation. So b squared times expected value of x minus mu of x quantity squared. This, of course, is just the variance. So the variance of y is b squared sigma x squared. Okay, so that means the standard deviation of y is the square root of b squared sigma x squared, which is b times sigma x. Note, if b is less than 0, then sigma y is equal to minus b sigma x. When we take this square root here, there are two solutions that lead to b squared sigma x squared, and that is plus or minus b. So if b is actually negative, then I have to take the minus sign in front of it, because if I don't, then I got a sigma y that is negative, and we cannot have a standard deviation that's negative. Okay, let's not worry about that just quite yet. We have a positive b, so this is just b times sigma x here for sigma y. So our correlation coefficient is b times sigma x squared over sigma x times b sigma x. And we see that that basically is b sigma x squared over b sigma x squared, which is 1 as expected. Note, if b was less than 0, then we would get sigma y as minus b times sigma x. And so our correlation coefficient becomes b sigma x squared over sigma x times minus b sigma x. And the b's and sigma x's disappear, but we got a plus 1 minus 1, doesn't disappear, so we get minus 1.0 as expected. And that includes our lectures for week 4. Thank you.